So now we want to continue our study of particle kinematics. We're going to look at some very specific types of motion. One is linear motion, so just if a particle is traveling along a straight line, what happens? And then we'll look at circular motion. What happens if a particle is moving in a perfect circle? So this rectilinear motion is where things are moving on a straight line. Uh, we don't always know position, velocity, and acceleration as a function of time. We might know, for example, acceleration as a function of position, but not explicitly as a function of time. Or we might know in a fluid, for example, the acceleration as a function of velocity. And based on what we know in terms of what other problems, then we have to work out some ways to determine position, velocity, and acceleration based on what we're given. So, as with the last lecture, if we're given everything as a function of time, we just take a bunch of time derivatives and that gives us velocity and acceleration. But if we're given, say, one component like acceleration as a function of another like velocity, we need some strategies for being able to determine velocity and position as a function of time. And we'll work out some ways to do that. So a little bit about notation and signs. Again, think about a particle just moving along a straight line. The position is referred to by the coordinate s. So s, for example, in all these cases that we'll talk about over here, s equals 0 is right in the center of the line. So positive s means the particle's out on the right, and negative s means the particle's over on the left. So the sign of s tells us whether we're to the right or the left of our origin. All right. Then we'll have velocity vector v and acceleration a. And what's important is that the signs of these are not related. For example, in this case, if the particle's out here and moving to the right, then s is positive and v is positive, right? But if we're out here and moving to the left, then s is positive because we're to the right of the origin. But if we're moving to the left, the velocity vector points left and v is negative. We can be back here. If we're to the left, s is negative. But if we're back here and moving to the right, then v is positive. Or if we're out here and moving to the left, s is negative and v is negative. Okay, so we can have all these cases, and they're not really related. They're pretty much independent of each other. Okay, so for example, what if we know a of t? How do we get the velocity? Well, that's pretty simple, right? Uh, we know that a is the time derivative of the velocity. So we can write a of t is dv dt. If we know a of t, then we just have to integrate this to get v, right? So if we take dv dt equals a of t, we can multiply through by dt in a sense, and we write dv is a of t dt. And then we integrate, and we get v of t is v naught plus integral t naught to t a of t dt. So if we're given the acceleration, want to know the velocity, you just integrate it. That is, if we're given the acceleration as a function of time, we just integrate it from t naught to t, and that gives us that v is v naught plus that integral. Okay. In a sense, what we're doing here is separation of variables, right? We're moving all the time, everything about time to the left and everything about velocity to the right. And we've got dv equals a of t dt. And we've separated the time variables and the velocity variables. And we just then integrate in a straightforward fashion. What if a of t is known and we want the position? Well, we just figured out how to get the velocity. If the velocity is the time rate of change of position, so v is ds dt, if we have the velocity, we can integrate that once to get ds. That is, we write ds equals v dt, just like this. And then if s equals s naught is the position at t equals t naught, then we can integrate s from s naught to s, v from t naught to t, and that gives us that s is s naught plus v naught times t minus t naught. plus this integral. Okay. Uh, by substituting for v, our result from before, v naught plus the integral t naught to t of a of t dt, then we can write this in terms of acceleration. So if we know the acceleration is a function of time and the initial position and the initial velocity, then we can work out the position as a function of time. All right, and from the slide before, we worked out the velocity as a function of time. So once we know a of t, we can figure out v of t and s of t in a pretty straightforward fashion, depending on how complicated this is and how easy the integral is. Okay. So we're going to do a bunch of integrals like this, integral t naught to t a of t dt. Okay, and this all works out if everything here is a function of either t or s or whatever. But we can't do it if it's mixed. So for example, if a is given as 3t squared plus 4v, and v is a function of s, then we can't just stick that in here and integrate over time, because v and s are functions of time in a way that's not given explicitly. And so you have to work on that a little bit more to be able to do problems like that. Okay, so for example, suppose we're given the acceleration, but it's only in terms of the velocity. How do we get the velocity? Well, if we know a is a of v and a is dv dt, then we write a equals dv dt. So dt is dv over a of v, right? So we've separated variables again. Everything over here is a function of velocity. Everything over here is time. We just now can integrate both sides. If v equals v naught when t equals t naught, so our v naught is our initial velocity at the time t naught. So then t of v is just t naught plus the integral from v naught to v of dv over a of v. So if they give us a of v, we can do this integral, and we know time is a function of velocity, and if we're lucky, we can solve for the velocity and we get velocity as a function of time. Okay, if we want to know position, then the point I was made before is that we can write s of v is s naught. Oh my, did I skip a slide? I did. Okay, so sorry. We worked out the velocity knowing a of v, right? So t is integral v naught to v of 1 over a of v dv. So that will relate velocity and time. If we want to know the position, then once we have t as a function of velocity, we can try to invert it and solve for v as a function of velocity. That may or may not be doable. It depends on how complicated a of v is, and therefore how complicated v of t will be. Okay, so we may or may not be able to solve that for v as a function of time, because what we have is time as a function of v. But we can also use this chain rule. So we can write a is dv dt, which is dv ds times ds dt, and ds dt is v, right? So this becomes v times dv ds. So the acceleration can be written as v dv ds. So we can write ds as v dv over a of v, right? So divide by a, multiply by ds. So ds is v dv over a of v, and from before we got we solved for that, right? So if our initial position is s naught for v equals v naught, then we can integrate this to obtain position. So s of v is s naught plus integral v naught to v of v dv over a of v. Okay. Now, how easy this is to do, in principle it's easy, but in practice it depends on what a of v looks like. All right, so what's tricky is that this doesn't give us position as a function of time. It gives us position as a function of v, but at least it gives us some information about our position vector, and with a little work we can work out the details of whatever problem we're solving. So let's look at another case. Suppose a is given as a function of s. That is, we know the acceleration as a function of position. Then again, we can use separation of variables. A is dv dt, which is dv ds ds dt, which is v dv ds. Okay, but now a is a function of s, so we'll multiply through by s, and we'll get a of s times ds, and we have v dv on the other side. So we separate the velocities from the positions, and then we integrate. So if equals s naught when v equals v naught, then we get integral v naught to v of v dv is integral s naught to s of a of s ds. And we're given a of s, so presumably we can do this integral and work out the velocity as a function of s. Okay, so after a little work, we can write that v squared of s is v naught squared plus twice the integral s naught to s of a of s ds. So if we're given a of s, we do this integral, we get v of s. So we can find the velocity as a function of position. If we want to know position versus time, what we can do is work out time as a function of position, and that gives us at least essentially the same information. So once we know v of s, we can again do separation of variables. V is ds dt, so dt is ds over v of s. And if s equals s naught at t equals t naught, then we can integrate both sides of this because we know v of s. So t of s is t naught plus integral s naught to s of ds over v of s. So we're just taking what we know on one side, all the common variables on one side and all the other common variables on the other side, separating those, integrating both sides, and then seeing where that takes us. Okay, now let's look at a specific case. What if the acceleration is a constant? Again, we're traveling in a straight line. We have constant acceleration. We can write down some simple formulas for those, and those come in handy sometimes. So for example, if you're looking at falling bodies and we ignore drag forces and things like that, then the acceleration due to gravity is, for all intents and purposes, a constant. So any kind of falling body problem where you're ignoring drag is a constant acceleration problem. So it's handy to have these simple formulas for cases like that. If the acceleration is a constant, then we can just integrate that once to get velocity and integrate that to get position, and we can find acceleration, position, and velocity as a function of time. And so it works out like this. If you do these integrations, then the velocity is the initial velocity plus this constant acceleration times the change in time, t minus t naught. So for any time, you can work out the velocity from this if you know the constant acceleration and the initial position in time, or initial velocity in time. You can integrate that once more and find that the position is the initial position plus the initial velocity times the change in time plus 1/2 the constant acceleration times t minus t naught squared. So at any time you can figure out the position from this. So we know the position as a function of time, we know the velocity, and the acceleration is a constant. It's sometimes handy to use this last formula. The square of the velocity is the square of the initial velocity plus 2 times the acceleration times s minus s naught. So this relates velocity and position and gets the time out of it. Sometimes that's handy. All right, so these are 3 handy formulas to know for any kind of problem where it's linear motion and constant acceleration. And so we'll make use of those as appropriate. All right. We'll use this chain rule in doing these kinds of problems and doing these kind of separation. We've seen some examples of this, so I don't need to go through it further. Now let's talk about circular motion. So that's kind of the basics of linear motion. Now let's say we have some origin O, and we have a particle that's just moving in a circle around that. You can think of this as a satellite orbiting the Earth, which is a circular motion, or other situations, a ball on a string that's being spun around, that sort of thing. Okay, so r is our position vector. Note that for circular motion, the magnitude of the position vector is a constant, but its orientation changes. So the position vector is just rotating around. So as the particle goes from this point to this point, the position vector rotates through an angle delta theta. So we can use this coordinate delta theta or theta to denote the position of the particle around the circle. All right. So given the radius of the circle of this motion, all we need to know about is theta as a function of time to know where the particle is. Okay, so we can define what's called an angular velocity, which is the time rate of change of this angle, right? So it's how fast it's spinning around. The units are like theta dots, or it's like radians per second. So we usually use the coordinate omega to denote angular velocity, and it's the rate at which this thing is spinning around, right? So it's radians per second. The time rate of change of omega is called the angular acceleration. It's the second derivative of that angle, right? So it's how fast this thing is accelerating or decelerating in terms of its rotation. So we can relate some of these coordinates. So we can define what's called a coordinate called S, which is the essentially the arc length as we go around here. So we can define the position as the distance traveled around this circle. And because it's a circle, this coordinate S is the radius times our theta coordinate, right? So if you know theta is a function of time, you can get S as a function of time, or vice versa. And these are related, right? So the time rate of change of S is R times the time rate of change of theta, because R is a constant, and theta dot is omega. So S dot is omega R. So if we know the rotational speed, we know the radius, then we can get S dot. Similarly, S dot is R theta double dot, which is alpha R, where alpha is our angular acceleration. So S dot turns out is the speed, right? The time rate of change of S is just this velocity vector VA. It's tangent to the circle because remember velocity is always tangent to the path. And so the speed is just omega R, which is the same as S dot. Okay, so if we look at some analogies between linear motion and circular, time is of interest in both. Position, in rectilinear motion we used S. Here we'll usually use theta. Velocity is V here and omega here. Acceleration is A here and alpha here. And the units are different, right? These are angular speeds and angular velocities. These are linear speeds and angular speeds and accelerations. Uh, and these are linear speed and acceleration. Okay. So let's do a quick example or two. Okay, so let's start with a decelerating car. So this is back to our rectilinear motion. A car is traveling down the road and all of a sudden jams on the brakes. We're told it takes 4 seconds to stop the car, and it travels 337 feet from the time the brakes were applied to the time that the car stops. Okay, if we assume that the linear acceleration is constant, then we'd like to know the speed of the car and the acceleration. Okay, the initial speed and the acceleration. And we want to express the initial speed in miles per hour and the acceleration in terms of g. So in terms of the acceleration of gravity. So if the acceleration is 2g, then it's accelerating at twice the acceleration due to gravity. It just gives us a simple way to kind of relate the velocity, the acceleration, to something we're familiar with, right? So we begin by noting that the velocity can be related to time for these constant acceleration problems, according to this formula we derived a few slides ago. Okay, so we let t naught be 0, so we assume our initial time is 0, and our final time is 4 seconds later because we were told it takes 4 seconds to stop the car. And our final velocity, that is at t equals ts, the velocity is 0 because we're trying to we were told it stops in 4 seconds. So if it stopped, that means it has 0 velocity, right? So we know the final velocity. We know the initial time is 0. We know the final time. So there's two things here we don't know: the initial velocity and the acceleration. So that gives us one equation for our two things we're trying to solve. All right. So 0 is v naught plus ac times ts, or v naught is minus ac ts. Okay, but that's not enough because we don't know V naught or AC. But we also know something about position. So the position S is the initial position plus initial velocity times the change in time plus 1/2 AC times t minus t naught squared. So we'll assume the initial position is 0. The final position then is d equals 337 feet, which is the stopping distance. Okay. And we know that it took 4 seconds to do that. So we know the initial time is 0. The final time is 4 seconds. We know all that. We don't know V naught or AC, but the final position is 337. Initial position is 0. Or no, the initial position here is 0. Final position is 337. So that gives the second position, which relates initial velocity and acceleration. We can combine that with this and solve for those two equations, two unknowns. We can solve it. All right. So if we put the numbers in here, then we get that this distance, 337 feet, is V naught TS plus 1/2 AC TS squared. So AC is minus 2 ds over TS squared. And we get minus 42.12 feet per second. Right? So they use this to eliminate V naught from here. They then just had an equation for AC, and they get it to be minus 42.12 feet per second squared. So now G is 32.2 feet per second squared. So we can use that to do this little conversion. So the acceleration is minus 1.31 G. So we're getting 1.31 G's, and it's negative, which means we're decelerating. So the acceleration is pointing back behind our velocity vector in the opposite direction. And it's negative because we're slowing down, we're decelerating. So that makes sense. Then we can, once we know AC, we can put it back in here and solve for V naught, and V naught comes out to be 115 miles an hour. Okay, so to work this backwards, if this car is traveling 115 miles per hour and decelerates at 1.3 Gs, then it takes 4 seconds to stop, and you travel 337 feet to in doing so. Okay, so by using those two equations that we worked out before, we could solve the whole problem. All right, let's do one more problem. So in this case, we have an object which is falling in a fluid, let's say water, and we're told that the acceleration is the acceleration due to gravity minus some constant times v over m, where v is the velocity and m is the mass of the particle. And this is typical, so that you can think of this as a drag force. As this thing travels through the fluid, there's a resistance to the acceleration due to the drag. And so the acceleration, which would be g in a vacuum, is reduced by this drag force, and the drag force is proportional to the velocity. So the faster you go, the more the acceleration is reduced. Okay, and we'd like to work out the position, okay, and velocity for that matter. All right, so this is one of those cases where we're given the acceleration as a function of velocity, and we have to use separation of variables to work out the velocity as a function of time and the position as a function of time. So we write a as dv dt. dv dt we can write as dv ds ds dt, or v dv ds. And then since a we know is a function of velocity, we want to get a over here with the v's and s alone. So ds is v dv over a. Okay, but a is this, g minus cd v over m. So if we put that in here, we get ds as a function of v. We can integrate both sides and we get s as a function of v. So the integral 0 to s of ds is the integral 0 to v of v dv over g minus this drag term. Okay, notice we've assumed that our initial position is 0, and at s equals 0, v is 0. So we assume we start at initial velocity, let go at s equals 0, and then see how it accelerates due to gravity with the drag term factored in. Okay, so this integral just gives you s because it's 0 to s. Okay, so then we just have to work out this integral. So we write it this way, do a little manipulation, you get down to this point. So s is minus m over cd times v plus mg over cd log of 1 minus cd v over mg. Okay, so this tells us the position as a function of velocity. It'd be nice to solve this for velocity and get velocity as a function of position, but it's kind of messy and that's not so easy to do. So all we can do is relate those two, maybe plot them, and then see how the velocity depends on s. Okay, so you can check your dimensions and that sort of thing. All this makes sense. Okay, so the only message here is that depending on what you're given, you have to separate your variables, get all one variable on one side, all the other variable on the other side, then integrate, and then you end up with results like this, which can get kind of messy, right? So that's the basics of rectilinear and um, circular motion.